Alright guys, so in this section we're going to be talking about the derivative and have a formal definition for what a derivative is. But first we're going to go back to our tangent line problem from before. So if you recall, when we discussed the tangent line problem, talked about the secant line getting closer and closer to the tangent line. If we take our definition of the slope of the secant line, you remember how that was the difference quotient, we can now think about not just approximating the slope of the tangent line, but actually using the limit process to come up with the actual slope of the tangent line. So if we take this definition here, the slope of the tangent line, I'm going to represent that with that m sub t, would be the limit of the slope of the secant line that we have here above as q gets closer to b. In other words, I can also represent this as this. So the slope of the tangent line would be the limit using the definition of slope here. This was the dy, difference of the y over the difference of the x, as this difference of the x is going to 0, right? So now this delta x for us is really this h right here in our diagram and in our graph. Here is the h really. So like in the following definition, we have a definition of tangent line with slope m, and this is exactly what I just described here. Now we're able to find the slope of the tangent line with this process, with the limit process, by taking the limit of the secant line as q gets closer and closer to b. Now that just means we're going to take the limit of this difference quotient here, which you have. Now the notation slightly different here is they use different letters, but the c here just represents the point here, x, in our diagram. So, we can relabel everything here, but to match this definition, it's basically just taking the limit of this difference quotient. As again, this delta x is just the h for us. So if I rewrite this with our variables here, with our constants, it would look something like this. So here we have it. Our slope, the slope of the tangent line now is going to be defined as the limit of this difference quotient as x goes to, as h goes to 0, right? And remember, this h is the distance here, the horizontal distance, right, from P to Q. But now as Q getting closer and closer to P is equivalent of saying H is getting closer and closer to 0, because as this distance shortens, then the closer Q is to P, taking the limit gives us the actual slope of the tangent line. Again, this definition here is exactly what we have here. If we were to relabel everything, it would look like this. So here we have it. Again, it's just a relabeling of the points here and the constants. Instead of our h, we have delta x. Instead of the x that we had before is the c. So that matches what you have in the definition here. But again, the idea is the same. Definition is the same. But this gives us the slope of the tangent line here. I'll probably use h instead of the delta x, but know that that's the same thing here. And instead of c, I'm going to use x. The notation just is different depending on the textbook or where you're reading it from. Okay, so this limit of this difference quotient is going to allow us to find the slope of a tangent line at a given point, or a line tangent to a function or to a curve at a given point here. So here's an example. Find the slope of the tangent line at this point, 3, -4 of this function here. So find the slope of the tangent line to this function at this point. So here we have our definition that we just got from here. And again, I'm going to use these letters here for simplicity. But remember that the h is just really that distance, that delta x that we had in here. As we already know, trying to direct substitute this 0 for h here is going to give us undefined here. Now, that doesn't necessarily mean that the limit doesn't exist. So we're going to try to algebraically manipulate this expression, or rewrite it in a different way so that we don't have the h in the bottom. And that's what you worked on in your algebra course with the difference quotient. So we're going to work algebraically the difference quotient so that we hopefully eliminate that h on the bottom in the denominator, and this way be able to find the limit. So after we expand everything, our binomial squares, and distribute the negatives, we see that some things cancel out. And notice here what's left is two terms that have h in common. So I'm going to go ahead and factor the h out. The limit now has been reduced. This expression has been reduced to just -2. The difference quotient has been reduced to -2x minus h, which, not having the h on the bottom, then allows us to direct substitute the 0 for h, and then we'll get a nice -2x. Now the -2x here is an expression. It's not the actual slope at this point because I haven't plugged in this point in here. Now notice how I could have done this whole process here with x equal to 3. So just plugging in 3 for x, and then done the same thing. The same things would have canceled out, and at the end I would have gotten -2 times 3, because that's my x right here from my point, and this would have been 6. So the reason I did it this way, because this gives us a general form of what we're going to be talking about in a minute, which is the derivative. So instead of finding just the slope of just that one point here, I found an expression that gives me the slope of the tangent line for any given x. And now from here, I can now just substitute or plug in my 3, x is 3 here. So then the slope of the tangent line would be equal then to -2 times 3, since 3 is the x, and that's 6. Okay, so graphically, guys, what we're talking about is if we were to graph this quadratic here, 5 minus x squared, this is roughly what it will look like, and the point 3, -4 would be on the graph here, obviously. You see now the 3, -4. So at this point, the line that is tangent to this graph at that point would have slope of -6, and I forgot to have the negative here. -6, and you can see how it's negative slope, and it's kind of pretty steep, so that agrees with a result here of -6. So that's what we computed here. So again, you could have done this from the beginning, plug in the 3 from here in your difference quotient, and then get the result of -6 at the end. But what we're going to be doing is finding the limit of this difference quotient in general, and so that we can now have a formula, so to speak, or an expression that gives us the slope of the tangent line at any given x, at any given point here on the curve or on the function. So this takes us now to our formal definition of derivative. Notice how that when we take the limit of this difference quotient, we get another function. In this particular example, this is linear, but we get a function. It turns out that this process, this limit of the difference quotient, is used to define one of the two fundamental operations in calculus, which is differentiation. So here we have the formal definition of the derivative of a function. So the derivative of f at x is, and we're going to use a couple notations that we'll talk about later, but for right now we're going to use this f apostrophe of x. So it looks just like your f of x with an apostrophe on the f there. It's equal to the limit again of this difference quotient, right? And we use this delta x as, we replace it with the letter h because we're used to seeing it that way for the difference quotient, but it's the same thing. Provided the limit exists for all x for which the limit exists, f prime, or the derivative of f, is a function of x. So this definition yields another function. Okay, so the derivative of a function, granted the limit exists, is a function itself. So here we have an example. Given this function f of x equal to x squared plus x minus 3, again another quadratic, let's find the derivative of x. And remember, the derivative itself is a function. So we should get an expression in terms of x, or a function of x. Okay, so using our definition, and again, I'm changing delta x for h here just for simplicity. But here's our limit as h goes to 0 of this difference quotient. Let's go ahead and plug everything in, evaluate this function at those inputs, and expand everything and see what simplifies. All right, so here we have it expanded here, and notice how once you've distributed your binomials and you have your signs distributed as well, you'll see that some things are going to cancel out, right? So this x squared minus x squared, the x minus x here, 3 with the negative 3, and then you end up with a few terms here that have an h in common, and again the same process is going to repeat. You're going to factor out the h and cancel it out. All right, so here we have it. Once we've canceled some terms out, the h goes away, then we're able to plug in this 0 for h, and then we end up with our limit, which ends up being now our derivative by our definition is 2x plus 1 of this function, right? So then we say 2x plus 1 is the derivative of this quadratic here, x squared plus x minus 3. Now again, we've seen one application, and that was our motivation problem, was a tangent line problem. So we're able to use this derivative to find the slope of the tangent line. If we're giving a point, we just plug it in here and have the slope of that tangent line at that point. So that's one application that we can use right away. We'll see later on many other applications in different fields how it is applied. As it turns out, the derivative can be used to find instantaneous rate of change. So for instance, instantaneous velocity or instantaneous speed at a given point in time, right? As opposed to just an average velocity. And we'll see problems like this later. We'll be able to determine what was our speed or velocity at a given point in time, at that specific instant in time, as opposed to, an average velocity from point A to point B. What was my velocity at that given point? So that's one of the many applications that we'll see where derivatives will come in handy. One of the nice results about the derivative is this nice theorem here, and very important to differentiability implies continuity. So the important thing here to notice about this theorem is the direction and the direction of this proposition. Notice the if, the condition, and the result. If f is differentiable at some point c, then f is continuous at that point c. So then notice how differentiability implies continuity. Now another way of saying the same thing would be the following. So if you have a function, a differentiable function, that automatically implies continuity, that the function is continuous at a given point, right? Obviously, you can extend this to a whole interval, but another way of saying this same proposition would be, it's what we call the contrapositive, saying that a function not continuous implies it's not differentiable, right? So basically, saying a function is differentiable implies continuity is the same thing as saying if a function is not continuous at a point, then it's not going to be differentiable. So these two are equivalent. So again, this is what we call the contrapositive here. Okay, so here we have the proposition and the contrapositive of it. Again, a contrapositive is always equivalent to a proposition. So if the proposition is true, then the contrapositive is also true. If a function is differentiable, then it's continuous. If a function is not continuous, then it's not differentiable. On the other hand, the converse of this proposition is not necessarily true. So in general, it's not going to be true. So this statement right here is not true, right? And the typical example is our famous absolute value function. Okay, so here's our example of a absolute value function, and we want to see what's actually happening at x equal to 0, right? Right at that sharp turn right there. Want to see if this function is differentiable there. Okay, so here we have a alternative limit of the derivative here, and I'm using this so that I can use, I'm getting ready to look at the one-sided limits as x comes from the left and from the right. And instead of using my definition here with the delta x or with the h, I'm using this alternative definition of a limit. One of the ways that I could determine whether this limit exists or not would be to evaluate the one-sided limits and see if they match. First, if they approach a number and if they're actually the same thing. All right, so here we have it. We want to see if these two one-sided limits exist and if they're actually equal to each other. So this is a pretty straightforward calculation because I can go ahead and evaluate f of 0. I know is 0 from our function here. And then f of x, depending on from which side we're coming, is either going to be negative x or x. Okay, so here we have it, guys. As you can see, we end up with the limit of, on the left side, as x goes to 0 from the left, of x, negative x over x. We're trying to figure out whether that's equal to the limit as x goes to 0 from the right of x divided by x. So you can see how the x's cancel out, and we end up with the limit. On the left, we end up with the limit of negative 1 as x goes to 0 on the left. And we have the limit of 1 here as x goes to 0 from the right. We already know the limit of a constant is just a constant. We can say now that negative 1 is not equal to 1. So then this shows that the limit doesn't actually exist. So the limit of this alternative definition of our derivative does not exist, which means for us the function is not differentiable at that point, x equal to 0. So I wanted to show you an example. This will be a counterexample to show that a continuous function is not necessarily differentiable. So we were trying to show here with an example that this proposition from the theorem does not work the other way. So the converse, in other words, is not true. Okay, a continuous function is not necessarily differentiable. Now, that doesn't mean that there could be a lot of continuous functions that happen to be differentiable, but in general, you can assume that. However, differentiable does implies continuity. So if we have a differentiable function, we have, by this theorem, we have a continuous function as well. So again, I wanted to show you this example. This is a typical function that you're familiar with, the absolute value function. And graphically, you can think of it as, well, if we're trying to picture the tangent line, the line tangent to this absolute value function, right at this point at 0, there's really an infinite amount of tangent lines that go through that point. We don't really have a unique tangent line here. And so that's going to give us the intuition of every time that you have a sharp turn on a function, whether it's just a corner like this, like in this V-shape graph, or when you have a cusp, or anything where the function turns abruptly, just changes abruptly, that's going to indicate the function not being differentiable at that point. Now, there's other scenarios. There are other examples, such as the f of x equal to x to the 1/3. So in other words, the cube root of x. So at 0, that function has a vertical tangent. So that's also going to indicate a place where the function would not be differentiable. So places like that where a vertical line has an undefined slope, or its slope is undefined, that gives us problem with the definition here of the derivative. So having a definition of the derivative gives us a better sense of smoothness, in a more rigorous way to show or indicate a smoothness on a function or in a curve. Just like we use our knowledge of limits to come up with a more rigorous and more formal definition of continuity on the previous sections. In the same way, differentiability allows us to identify smoothness of functions, and we would also have graphical representations on when a function is not smooth, it's not differentiable at a certain point. So again, here's an example of a continuous function that is not differentiable at a point, and we've showed it here with our definition of the derivative with this alternative form of the limit definition of the derivative. This allowed us to compute the two one-sided limits and be able to determine if the limit actually exists. And as it turns out, it doesn't. So then we conclude that the function is not differentiable at x equal to 0, this absolute value function. And again, graphically, you see that with a sharp turn. So that's going to indicate that the function is not differentiable there.